Today we are here with Dr. Bin Liu. He did his BS and MS in physics at Shandong University in China and then moved to Cleveland, Ohio, and got his PhD degree from Case Western in 2018. He then had 2 3-year postdoc positions, first at the City University of New York and then at the University of Michigan in Ann Arbor, where he was promoted to assistant research scientist in 2024, and that's the position he holds now. His research is in the areas of quantum light matter strong coupling, nanophotonics, low-dimensional quantum materials, optoelectronics, nonlinear optics, and ultrafast spectroscopy. He has authored or co-authored over 20 publications and also has a patent on artificial photosynthetic devices utilizing polariton antennas. Today he will talk to us about light matter strong coupling in organics and 2D quantum materials for fundamental physics and device innovation. So no matter if you are here for the fundamental physics or for OLED TVs that last longer than the current generation, please help me welcome Bin Liu.
Thank you. Thank you for the introduction. All right. Okay. Good afternoon, everyone. Oops. I can just hold it. Yeah, good afternoon, everyone. My name is Bin Liu. Currently, I'm working in the Department of Electrical Engineering at the University of Michigan. So today, I would like to talk about my research work on the light matter interaction in organics and 2D materials for fundamental physics and device innovation. So hopefully, I can give you a picture, on this kind of topic. All right, so first I would like to quickly introduce light matter interaction in photonic and optoelectronic structures. So this is a kind of like a combined system. We have the photonic structure. For example, we have optical cavity, we have the photonic crystal, or we have some plasmonic structure. And for the material side, we have atoms, we have organic molecules, we have the low-dimensional material. Okay, so then due to the interaction strength, actually we can classify different coupling regime. So one of the coupling regime we call weak coupling, which means, okay, the interaction is not very strong, it's very weak. So later I will, give more details in how we define if it's weak or strong. So in this interaction regime, because the interaction is so small, actually it's only give us a perturbation term for the interaction. And the transition rate will be dominant by the golden Fermi rule, the Fermi golden rule, and the Purcell effect will be the key effect in the structure. So you can imagine if the light matter interaction becomes larger and larger, we can enter a new regime. We call it a strong coupling regime, strong light matter coupling regime. Now let's do a little bit about the math. We can write down the light matter interacting Hamiltonian for the system. So from here, you can see I have non-interacting 2 terms, the H naught, and I have an interacting term. So if the interaction term is very small, which means much smaller than the non-interacting term, so basically it's just a perturbation term. And also the coupling strength G will be much smaller compared to any loss of the non-interacting exciton in this case, or the photon, okay? So this is the weak coupling regime. If the G is large enough, we cannot treat this term as a perturbation term. So we need diagonalize the Hamiltonian matrix. We can solve the equation and find out the new eigenenergy for the new eigenstates. So here you can see we have a higher energy level, we have a lower energy level. Okay, so if for the resonance condition, which means in this case exciton has the same energy as a photon, right? So we can find out the smallest energy difference between the E plus and E minus. So we call this energy difference as Rabi splitting energy. Okay, and in this case, we will have a new quasi-particle. We call it polariton. In this case, we use exciton strongly coupled with photon, so we call it exciton polariton. And also, people also use vibrational mode or molecule, that's phonon, right? So you can also get phonon polariton. Okay, and I will focus on exciton polariton. And the exciton polariton actually is a hybrid light matter states. Okay, I will introduce more property for this quasi-particle. So first of all, energetically, you can, due to the strong coupling, you can form exciton polariton. You will have new eigenstates with new eigenenergy. So the state with a higher energy, we call it upper polariton. And the one with lower energy, we call lower polariton. So energetically, you can have new energy level formation. Okay, and also, how do we characterize the exciton polariton? So we need to characterize the very particular energy momentum dispersion relation. So let's take cavity exciton photon polariton, for example, which means my photon is provided by a optical cavity. Okay, so the blue curve in the figure on the right is the exciton dispersion. So there's no dispersion. Okay, and the right dashed curve shows the cavity photon dispersion. It's pretty or parabola curve, and due to the strong coupling, so these two dispersion curves will disappear. Instead, we have the new dispersion curve, the upper one and the lower one. So these are the characteristic property of cavity exciton polariton states. Okay, and we call it anti-crossing dispersion. So in order to demonstrate polariton, we need to show this anti-crossing dispersion. So that's step one. Okay, and we know this is a hybrid light matter states. So which means for both the upper and the lower polariton states, it's a hybrid state. It has exciton component. It has photon component. So here, the coefficients alpha, beta determine the excitonic fraction and the photonic fraction in the hybrid states, respectively. Okay? And we also define the deturning, which is the energy difference between the uncoupled cavity mode and the exciton mode, right? So which means the upper and lower polariton will be a function as the deturning. So for example, at the resonance condition, at these two very special points, so this is a cross point between the exciton and cavity photon, so which means the upper and the lower polariton will have 50% fraction of exciton and 50% of photon. And then for the upper polariton, if you go to a larger deturning, it will be more photon-like, right? But instead, the lower polariton will be more exciton-like. Actually, we can play around with this kind of contribution in order to realize some specific application. I will give you some example later. Okay. Okay, so now I want to quickly introduce the history about the study on this topic. So in 1958, John Hopfield first introduced the polariton concept in solid states. Well, I know in 2024, he won the Nobel Prize due to the work on artificial neural network, right? Well, actually, back to 1958, he first proposed the polariton. And then people demonstrate exciton surface plasma polariton in 1982. Okay? And later, people also experimentally demonstrate strong coupling between atoms and resonant cavity. But in this case, they use a millimeter cavity mode, which is not optical cavity. And in 1992, okay, so people use inorganic quantum well exciton strongly coupled with the optical cavity. and demonstrate the cavity exoplanarton. And because most of my work is about organics, and in 1992, one group from UK, they demonstrated strong coupling by using organic molecule with the optical cavities. And another thing I would like to mention, until 2012, people demonstrate strong coupling, show the cavity polariton by using the transition metal tetracogonized monolayer exciton within the optical cavity. Now, many material candidates are used to demonstrate the polariton. I think the real question is, what's the key advantage of the polariton? I mean, besides some fundamental physics, if the polariton can introduce some benefits for the device application. So that's the real question. Okay, so we know the exciton polariton provides a very promising platform for fundamentals of physics study and device innovation. Okay. And here I would like to highlight some very unique property of the exciton polariton. Actually, as I said, exciton polariton is a hybrid light matter states. It can inherit the property from both the material side and the photonic side, right? So for the material side, we use exciton, so which means it will give us electronic response. And also it will have very large electron-electron interaction, which give us the scattering behavior. Also, it will give us some optical nonlinear response. So that's the advantage or key feature from the material side. For the photon side, we know there's no mass, which means a very small mass, right? So, and then it will provide spatial coherence. And you can have some interference fringes, if you design some structure. And also, it can provide long-range propagation. So this will be very useful for long-range energy transport, okay? So basically, as I said, polariton is a hybrid state, right? So actually, we can, based on this property, we can choose which polariton states we will use for particular device design. Okay? And I will give you a few examples. The first one is polariton condensation. But we know people first, when the Bose-Einstein condensation was first predicted, right, until 2002, I think, and people used, atoms to realize condensation. And a very low temperature, probably nanokelvin, if I'm correct. But people use this polariton. They show polariton condensation at 5K. It's kind of like a little high temperature, right? So compared to the atom case. And also, people demonstrate electrical pumped polariton lasing. So this is a very, big breakthrough. And it can be used for some real device, right? So optical pumped laser, I think is fun because you have to pump the device, right? But in this case, if you just apply the voltage, you get lasing. I think that's a pretty good advantage for a laser device design. And in this case, but until now, only inorganic quantum well is used to demonstrate electrically pumped polariton laser. So organic still cannot achieve that. But organic polariton already show the polariton condensation even at room temperature. So this is the advantage of organics. And also, people demonstrate the optical polariton transistor. Basically, you can see the signal can be enhanced due to the polariton. Okay, so these are three, typical application, device application or device demonstration I would like to mention. And but for my talk, this is the outline, and I will try to cover the research work I have finished. And so first, I will talk about the linear and nonlinear optical property of exciton polariton in FiberPro optical microcavities. And the second part, I will talk about the long-range propagating exciton polariton for photonics and optoelectronics. And the third part, I will introduce a very advanced technique. We call it ultra-fast spectroscopy to study the ultra-fast dynamics of the Polariton system. So finally, I will give you a summary and give you an outlook for my future research work. And just as a reminder, so this is the key property of the Polariton, right? Due to the excitonic and photonic components, my talk will cover mainly about these three. So the optical nonlinearity, the long-range propagation, the spatial coherence. Okay, definitely I will talk about the energetic, energy splitting. So that's the starting point of the Polariton. Okay. Now let's go to the part one. I will talk about exciton Polariton in coupled double microcavities. Okay. So actually, this is my first paper for my PhD study, and I'm the first guy to study Polariton in my group. So, but anyway, yeah. So I designed the cavity. This actually, you can see there are three metal layers. That's why there are two microcavities. The first one is a symmetric cavity. You can see the organic material within the cavity are the same. The second one is a non-symmetric cavity. You can tell the transparent layer will not provide exciton. Only the second layer can provide exciton. Okay, so this is the dye molecule I use from our collaborator. Okay, so then now we need to demonstrate cavity Polariton. That's the step one. Okay, so how to do that experimentally? So we can check the reflectivity spectra by changing the angles. So you can see physically, I change the angle and I measure the reflectivity spectrum. At each angle, you can see 4 reflectivity dips. They represent the Polariton modes. Okay, and how to explain the experimental observation? So, but before we get there, we need convert this data to the energy momentum dispersion data, right? So in order to show the dispersion. So what I have done is at particular angle, which means the angle also give you the momentum information. We know 2 pi over lambda times sin theta. Yeah, that's the wave vector, right? So actually we can find out the energy location for each Polariton states at a particular angle or particular momentum. Then I can plot these curves or the data points. Okay, so I can plot this, the lower energy one, middle energy 2, and then the lowest one. Okay, you can see there are 4 branches. So I mean, probably you will ask, oh, previously you showed just 2 branches, one for upper Polariton, one for lower Polariton. Why there are 4? Okay, so we need a model to explain. So because it's a double cavity, so therefore the optical cavity will be strongly coupled. It will give you the symmetric cavity mode and anti-symmetric cavity mode. And then the organic exciton will strongly coupled with cavity modes. I mean, it just become a little more complicated actually. So by solve this equation, you will have 4 eigenenergy for each eigenstate. So that's the curve shown in figure B. So which means in the double optical cavity, we have 4 branches. It's due to the strong coupling between organic exciton with the 2 optical cavity modes. Okay, and then when we talk about the non-symmetric one, okay, what's the difference? Okay, and but I can shine light from the top and then measure the reflectivity. So this is what I got. So for each angle, you will see there are 3 reflectivity dips, which means there are 3 Polariton states. If I shine light from the, I also try to convert to the dispersion relation in order to show Polariton. And then I can also shine light from the bottom, okay, check the reflectivity spectra again. But see, now you can see for this case, there are only 2 Polariton states, right? So this means the Polariton, based on the non-symmetric cavity design, the Polariton will introduce the optical symmetry in this coupled cavity structure. So all the study is in the steady state. So just show polariton. And and then I will talk about the nonlinear optical response due to the cavity polariton. So, I mean, if you take some nonlinear optics class, and we can write down the total polarization, the linear term, the nonlinear term, right? So, and actually, for all the material, so for the chi2, that's a second order. The second order nonlinear term depends on the symmetry, the central symmetry. You have to break the central symmetry, otherwise they will counter-interact with each other. And all the material will have the chi3. They don't need any symmetry. So that's the nonlinear optical process I have studied. So we call it the third harmonic generation. So which means you shine a light. It's a laser light, and with a particular wavelength. And if due to the third harmonic generation, so the wavelength will become shorter, just lambda divided by 3. The energy will be tripled, right? So that's the third harmonic generation process. And so that's only for the material part. Because we introduce the cavity, right, it will change the parameter. So the question we try to answer is if the polariton will surprise, enhance, or do nothing about the optical third harmonic generation process. So that's the question I try to answer. So again, this is, and the sample, is a little simpler. It's just a single cavity. So that's not a double cavity. And again, first I need to show the anti-Croton dispersion. The figure on the left shows the upper and the lower polariton. Okay, that's good. And then I do the angle resolved third harmonic generation measurements. So for each pump wavelength, I can vary the angle in order to check the third harmonic generation signal. So you can see the peak value for a particular wavelength occurs at a certain angle. Okay, if I plot the peak value, the peak angle value with the linear response, actually it will fall within the upper polariton states. So which means the upper polariton enhance the third harmonic generation signal. So yeah, this is an experimental observation, and then we try to understand. So then we just use this. We use nonlinear transform matrix to model the chi3, the third order nonlinear coefficients. We sum up all the polariton states, and we do the calculation. Actually, so these are the calculation results. We can compare the figure on the left and in the middle. So they agree with each other pretty well. And again, we can calculate the pump wavelength dependent response. So all the data fall into the theoretical prediction. Okay, so which means the exciton polariton represents a fundamental excitation to enhance the nonlinear optical response. Okay, so now we know, okay, the polariton can give us the energy splitting. The polariton can give us enhance the nonlinear optical response. So my another work is about, okay, instead of a cavity, can we use some other photonic structure to study the polariton, to demonstrate polariton? Okay, so this work, I realized strong coupling between the cavity polariton with the time plasma. Okay, time plasma is formed at an interface between the metal and a one-dimensional photonic crystal. You can also call it a distributed Bragg reflector, or DBR. So this particular mode will locate within the light cone. Light cone is defined by the dispersion relation, K equals omega divided by C. That's a light line. And so this mode will be within the light line. Okay, and also it has both TE and TM polarization. That's the electric field of the direction of the electric field of the mode, and it can support the in-plane propagation. Okay, and if I put the cavity polariton structure onto the time plasma structure, what will happen? Okay, so now I want to just, before we talk about the data, I would like to introduce a technique. We call it Fourier space imaging. Because previously you can tell, in order to resolve the dispersion relation, I have to physically change the angle, right? But now if we use Fourier optics, we don't need to do that. We just use the Fourier optic component. For example, just the lens, to get all the information in the momentum space. So that's the advantage of Fourier space imaging. So basically, we call it a 4F optical system. So in the real space, you can get a clear image. That's a real space. But in the K space, you will get all the information about the angle theta. And again, theta represents the momentum information, right? So yeah, and then we use the CCD camera to record the information about the angle in this direction. And probably another direction, we record the wavelength or energy information by using diffraction grating. So that means by a single shot, we can get the polariton dispersion information. Let me show you the example. Okay, so yeah, we have a cavity polariton. If we use the Fourier space imaging, we will get that figure. I mean, that's just a single shot. I don't change the angle physically. But we can still, get all the angle or momentum information. And we have the upper polariton, we have the lower polariton, which is the dark line, dark area, and the solid line or the theoretical calculation. Okay. And this is the real sample. We know the time plasma will strongly depend on this layer. Actually, you can shift the time plasma by changing this intermediate layer thickness. So if it's too thin, actually, figure B shows time plasma at this position. It's far away from the cavity polariton. So there will be no strong coupling. There will be no coupling between the cavity polariton and time plasma. Once I increase the silicon nitride layer, okay, I will shift the time plasma to a lower energy position until it can interact with the cavity polariton. Now I have 3 branches, okay? The higher and the upper one, the middle one, and the lower one. That's due to the strong coupling between cavity polariton and the time plasma. And I can keep increasing the silicon nitride layer thickness. So now you can see, you will blue shift the whole spectrum. All the modes will, red shift the whole spectrum. Okay, so the part 1, I just introduced some a different photonic structure, give you different polariton states. And part 2, I will talk about the propagating polariton system. I have been working on this system and developing this system for the last 4 years, and for both the fundamental physics and also some device demonstration. And I will pay more attention to these the work. So this particular polariton system relies on Bloch surface wave. Bloch surface wave is supported by a one-dimensional photonic crystal, and it's a surface wave. It can propagate in the plane over a longer distance. Okay, and differently from time plasma, the Bloch surface wave only exists beyond the light line. So just as a surface plasma polariton is also beyond the light line, and it can provide long-range in-plane propagation. Okay, so how can we see or how can we measure the Bloch surface wave? Okay, so once we have this structure, again, we will do the angle resolved reflectivity measurement. Okay, we use the Fourier space imaging, get the single shot of the imaging. On the left shows you the experimental results, And you can see we have a very narrow dark curve at the edge. So actually, +1, -1 define the light line. Okay, beyond the light line, which means it's smaller than -1 or larger than +1. Okay, so this is the BSW mode. Is a pure photonic mode. By the way, the left shows the simulation results. You can see the good agreement. Okay, so once we put some excitonic material on top of the BSW structure, if the interaction is large enough, we will get strong coupling. So that's a concept. Okay, so this is the system I studied. I put an organic molecule prepared by thermal evaporation on the DBR structure. Okay. And I do the same thing. I use the Fourier space imaging to check the reflectivity. And you can see, hopefully you can see, this is my lower polariton. This is my upper polariton based on the simulation. But experimentally, because due to the low resolution, so the upper polariton might not be detectable. So, but the lower polariton is pretty obvious. Okay, so we demonstrate the polariton. We can also check the angle resolved photoluminescence, to check the polariton emission. Okay, it will follow the polariton propagation, polariton dispersion. Okay, now can we use this polariton for some device? Yes, we can. So first, I will talk about the photosynthesis. So what we can learn from the nature. Okay, so if you talk about a leaf, actually it can give very efficient. It undergoes very efficient photosynthesis process, right? Because all the molecules are very well highly ordered superstructure, right? It can absorb the solar energy. It will transfer the solar energy by the antenna molecule to the reaction center. Then the solar energy will be stored as chemical energy, right? So that's how it works. But we cannot mimic this process very efficiently because, first of all, most of all the organics are Franco exciton, which means they are strongly localized, and the transfer process is undertaken by Hoping process. Is strongly surprised the Hoping process can only happen shorter than 10 nanometer. So that's reason one. Secondly, we cannot avoid any defects or disorder. So different from the nature structure, a natural structure, and all of these will make the process non-efficiently. Okay. So our method is we know this BSW polariton can support long-range energy transport. We will try to realize this process. Okay, so this is the structure, the device I made, and so I put an organic molecule on top of the DBR structure, which plays the role at the antenna or the polariton antenna, and this is my reaction center. It's kind of like a solar cell. Okay, so the idea is once the polariton, absorb the light, give the energy, it can be carried or transported by the polariton. Okay, until the energy is transferred to the reaction center. So basically the donor acceptor heterostructure in the reaction center, and then the photon energy will be conserved to charge, collected, and generate photocurrent. So that's the process. Okay, but first we need to make sure the polariton can really support the long-range propagation. So here I just check the PL distribution as a function of wavelength. Actually, you can see it can support the propagation over 100 micron. It's pretty long, right, compared to the exciton Hoping process. Okay, the Hoping process only occurs like 10 nanometer. Okay, and then I also made several control samples in order to compare with my polariton device. Control one is there's no DBR, which means there's no block surface wave, okay? Only organic here. So which means the exciton just hopping for energy transport. So the control 2 is there's no organic molecule, just a DBR for this area, which means it's just a pure photonic structure. So then I shine the laser light onto this area, and then I can measure the photocurrent, the GV the photocurrent density voltage characteristics. Okay, and if you compare the units and the amplitude, actually you can see the polariton device is very efficient compared to the other two control. And I can also check the EQE, the external quantum efficiency of the device, and also the responsivity of the device. Okay, it follows the exponential decay. So when the distance becomes longer and longer, the EQE will become smaller and smaller. It follows the exponential decay. Okay, so that is one example for application. So the other one is if the similar results can be achieved by using some 2D monolayer material. Okay, so I use the WS2. It's a typical layered TMD material. So people study it because due to the very fascinating property of the TMD. Okay, I will not cover all of this. And then again, the limitation is for TMD exciton is also a Frankel exciton, and for the exciton, the transport is very short. And also, people always use some flake, so the area, the size is limited. But for my study, I use large-scale CVD growth WS2 and try to study the long-range propagation. Okay, so again, I can change the DBR structure by increasing the number of the dielectric pairs. In this way, I can enhance the propagation. For example, BSWP3 means there are only 3 pairs of, let me go back. There are only 3 pairs of the dielectric materials. And I can get the Rabi splitting, I can get dispersion. And then as the number of the pairs keep increasing, actually you can see the interaction become larger and larger. It also will affect the propagation behavior. You can see here, this is a real space PL imaging. And very clearly, you can see the BSWP6, which means the DBR has 6 pairs. It propagates much longer compared to the all the other 3. Okay, and we can also get the wavelength resolved propagation information, and then we can get this plot. So basically, there are 2 conclusions. First, in order to increase the propagation, we can increase the number of the DBR pairs. It will help us to make the propagation longer, and also the BSW fraction, which is the photonic fraction, will also help to increase the propagation. So you have 2 knobs to change the propagation. Okay, and next I will quickly cover some other structures. And so the BSW structure is pretty nice for propagation. Actually, we can patterning, we can engineering the structure. Okay, so for example, we can do etching to make some stripe. And then in that way, we can confine the polariton within the structure. For example, this figure, that's an infinite DBR structure. This one shows the PL distribution in the K space. You can see it's a pattern structure. It's strongly limited, confined the polariton states. Okay, actually, because the width of the polariton, the width of the pattern is pretty long. It's over 4 microns. It's not a single mode. It's multiple mode, right? So I show you the simulation. Actually, we have a fundamental, first order, third order, and fourth order modes. Okay? And again, we can check the PL distribution, which gives us the polariton propagation information, and it will strongly confine along the stripe, along the pattern. Okay, and also we can define the propagation direction. So, for example, in this case, the cross shows the pump spot. We can check the polariton signal at the edge marked by the circle area. And you can see the polariton only exists at this direction because we select the direction by focusing the checking area, right? So, and we can also make the distance between the pump and the detection area longer. We can still see the polariton, the signal just become weaker, okay? And if we check the top end, actually we can see the polariton from the other side. Again, because we are selecting the signal, which means we can control the direction of the propagation. Okay, now also we fabricate this structure. It's a typical Mach-Zehnder interferometer structure, and you can see the scale, and it's in the micro scale. And then we study the emission distribution, and so the point is, if the coherence is maintained by the polariton, we will see the interference information in interference fringence. Actually, yeah, we really find the fringent interference feature, and also it's wavelength dependent. So because the polariton is also wavelength dependent, it will have different photonic fraction. If you have more photonic fraction, the coherence will be maintained better. Okay, and also we do the calculation. We get pretty reasonable agreement between the theory experiments. But again, due to the length, because the length is about 3 micron, it's not single mode. So we believe if we can downsize to single mode, the signal will be more stronger, will be more clear. So, but this is a multi-mode structure. Okay. All right. So now I will switch to the ultra-fast part. But I know it's kind of probably that's new for you guys, and I think I will just quickly talk about the key observation or the conclusion, right? So I will not cover too many details. Okay, I use ultra-fast spectroscopy to study different cavity polariton or some other polariton system. I mean, from the material side, I use TMD, I use organics. And today I will only focus on the TMD. And if you are interested, you can check this paper, all of this my paper are about organics, organic-based polariton system. Okay, so why we use ultra-fast spectroscopy to study the polariton dynamics? Okay, first of all, I didn't mention previously, but like in order to achieve strong coupling, we have to use a large number of molecules, and which means it's not a single molecule, and we call it collective strong coupling. So in that case, let's say we have n molecule, we have 1 photon, then we have 1 upper and 1 lower polariton, and n-1 the localized states. We call it exciton reservoir or dark states. So these are localized states. It will not give you very ultra-fast response, and it will not help you to provide any polaritonic effect. So this will be the limitation, when we talk about collective strong coupling. So the point is we try to use ultra-fast spectroscopy to show the intrinsic polaritonic dynamics, and it will be very helpful to design the device. Okay, so yeah, in order to answer, these are questions we try to answer. The role of the exciton reservoir in the dynamics. And second is, does the dynamics depend on the pumping scheme? So, which means non-resonant pump or resonant pump. The third one is, okay, we try to show for the first time the intrinsic ultra-fast polariton dynamics. So that's the 3 questions I try to answer. And specifically for organics, due to the spin statistics, we have singlet, we have triplet, right? So how to manipulate these spin states, it will be very crucial for enhancing the device performance, for example, the organic solar cell and the organic LED. Okay. All right, so yeah, so the polariton dynamics, because due to the photonic structure, we need the time resolution in the 5 femtosecond regime. So, which means we cannot use regular camera. The response speed is not fast enough. So we have to use the ultra fast spectroscopy, and it can give us the 5 femtosecond resolution. Basically, you will use the physical delay line, and determined by the speed of light and the distance, you will get the 5 femtosecond regime instead of electronic response. So the electronic response, as I know, probably the street camera can give you a resolution like probably 10 picoseconds. If any dynamics within picoseconds, you have to use ultra-fast spectroscopy. Okay, so this is a nonlinear optical characterization technique, and you have a pump beam, you have a probe beam. It undergoes the third order nonlinear optics, and you will check the change of the probe beam in order to characterize the dynamics. Okay. Okay, I will quickly show you the results. If you are interested, we can talk about more after the seminar. Okay, I studied the TMD polariton system, and as I said, for the resonant pump condition, it's very crucial. And first of all, I need a prism coupling because BSW polariton only exists beyond light cone. So I need to provide some coupling technique in order to match the momentum requirement. Okay, and also I need to select the angle and the wavelength very well for the pump beam. So for example, if I try to detect this angle, try to use this angle for the pump, so my wavelength should be exactly at this number. So otherwise, the resonant condition will not be met. And for the probe, I can just fix an angle and using a white light to check it. And we can check the change of the probe beam, the intensity. Okay, and for comparison, I also use, I call it above exciton pumping. So it's a non-resonant pump. Okay, and so this is just as an introduction. So this is a pretty typical contour mapping for the transient absorption spectra for the SS2 monolayer, for the bare monolayer. And you can see some blue color. So that's due to the ground state bleaching of the exciton of the SS2. It's not about polariton, just exciton. And you can see it's around 610 nanometer. So that's the exciton wavelength. If I pump using 635, because there's no real exciton population using this lower energy pumping, there's no signal at all, right? So, but when I use 500 nanometer, I go to a higher energy level, it will decay to the polar exciton. So that's why I have that feature, okay? So, and based on the literature paper, we can analyze the kinetics, we can get all the time constants for the control sample. And then I move on to the polariton sample, study the polariton at different angle. But I think I just skipped that, due to the time limit. So the key information I try to deliver is, so under the non-resonant pump, so the exciton reservoir dynamics is just to follow the bare exciton. There's no change at all. But if we do resonant pump, actually we will find some ultra-fast feature. So because the dynamics really depends on the pumping scheme. So for the above exciton pumping, actually you pump the exciton to a higher energy level. It will relax to the exciton reservoir and then populate. Okay, one part will just decay. Okay, it will give us the exciton dynamics, and one part will populate the polariton states, and the polariton state will decay. So which means at this pumping scheme, the exciton reservoir will follow exactly the same dynamics as the bare exciton of the control. But for the lower polariton resonant pumping, actually we resonantly excite the lower polariton. It can undergo coherent population exchange with the external reservoir and then decay. So this process is very short. So that's why we get very ultra short dynamics. And then the lower, it also relax to the probed Polarton states and then decay. But I know it's pretty complicated. And the information I try to deliver is by using the ultra-fast spectroscopy on the different pumping scheme, it can provide efficient pumping scheme for your device. For example, it can be used to lower the lasing threshold for the Polarton device. Okay, so this is my summary. And so far, I have used organics and TMD materials, and also the optical cavity photonic crystal to realize strong coupling. I think I cover the hybrid light matter states concept, the enhanced nonlinear optical property, the long-range energy transfer, and the long-range coherence. Also, I cover a little bit about the ultra-fast dynamics. So, I mean, for my future research plan, I would like to study some more material candidates. For example, some other low-dimensional quantum material, including 2D magnets, and also layers perovskite. So it also has a very well-defined in-plan structure. And for the photonic platform, I would like to study some plasmonic structure, like a metallic nanoparticle array or some metal surface. And so in order to do more study based on the Polarton property, such as due to the quantum nature and delocalization of the Polarton, if the material property can be efficiently modified. So some theory predict the conductivity can be increased due to strong coupling. But we know conductivity is a very, very important key quantity for the device, right? So I would like to design some and take some very comprehensive study based on the photonic system design. Also, I would like to develop some other photonic structure. For example, the BIC state, which is the bond state in the continuum, it will provide a high quality factor. It will further enhance the light matter interaction. So hopefully it can lower some threshold for some device performance and also give us some exotic physics phenomena such as Polarton condensation at very high temperature with low threshold, and also superfluidity. So, and also for some photonic integrated circuit application. So all of these will help us to get a better understanding for fundamental physics and nanophotonics. And also recently, I mean, in the last 3 or 5 years, people propose a new topic called Polarton chemistry. They claim they can change the ground state. They can modify the reaction rate, chemical reaction rate. But I think there's still some argument about that. So this is another topic. The third thing is how to use this concept, combining the advanced photonic platforms to further increase the micro-nano photonic optoelectronic devices efficiency. So I think that's all. So I will stop here, and I will be glad to take your questions. Wait, slide 7, right? Okay. That's my old work. Okay. Well, sorry, what's your question? Okay, so for this specific case, the silver is very thin layer, right? It's made by the high vacuum thermal evaporator. And the organic, in this case, I do spin coating. Okay, that's my first work. And we also do, high vacuum thermal evaporation using for the organics. Yeah, and I think so. If we, based on the interested wavelength range, right? If you study like longer wavelengths, you probably want to use gold instead of silver. It will play the role as a mirror. And for gold, as I know, it's better to use E-beam evaporator, right? It will give you smoother surface. Yeah, and also, okay, and you can, instead of a metallic mirror, you can use a dielectric mirror, the DBR. And for those structure, I use a PECVD, plasma enhanced chemical vapor deposition method, just multi-layer structure. And I also responsible to make some transferable DBR for my collaborator. So like we use zinc sulfide and magnesium fluoride, and due to the adhesion force between the zinc sulfide and the substrate, actually you can transfer the DBR, because my collaborator, they don't want waste of the sample. If I make those samples, they can use the flake and transfer it, for a long time. So yeah, I mean, you can use PCVD, you can use a thermal evaporator to prepare the dielectric mirrors. Yeah. Sorry. What? Do you know the slide number? Oh, okay. Yeah. So because recently we just submitted a paper, we used TMD. For the TMD, actually, it's not a real spin. It's a pseudo spin. It's due to the spin orbital coupling. For the TMD material, you have different valley, and people just use a pseudo spin. And under different magnetic field direction, actually you can selectively pump, select the spin. And so my future research plan is, for example, if I use 2D magnets, actually I can use the magnetic field to control the polariton and to study how to energetically control the splitting. Secondly, if I can do some like a dynamic study by applying the magnetic field, give me some information in the time scale. So that's I mentioned. So it's very material dependent. So the 2D magnets might be very interesting for that study.
If you had circularly polarized light or left or right-handed polarized light, or if your molecule had like a left or right-handed symmetry.
Okay, so for organics, it's hard because this kind of helicity is very small. But actually for TMD, yes, we call it a valley polariton. So my previous lab, back to City University of New York, they use circularized white light to characterize polariton. And also the valley information can be maintained by the polariton. So again, remember, the polariton is a hybrid state. It can inherit this property from the material side. And because the TMD, it has a valley information, the helicity, it will have different response for the circular polarization light. And the polariton, yes, it can inherit that. But for organics, I try to do that, but as I know, it's so small. The difference is so small compared to TMD. It might be within the error bar. We cannot see or we find that, right? So yeah, I mean, I know for OLED study and people, in some group in China, they try to fabricate this. They try to synthesize some material, organic materials, in order to increase the helicity. But I still think it's too small if I try to use for the polariton. Yeah. Yeah. They're very difficult. Yeah. Oh, so okay, because the source and usually at the bottom, and the sample is on the top, and the substrate there's a substrate, right? Probably like I will say, we put some thermocouple to measure the temperature. I mean, if it takes a long time, probably it goes to like 30 or 40 C. So it will not, as you know, as I know, it will not damage the organic molecule. Yeah. Yeah, that's a very good point. Yes, yes. So first, in order to achieve strong coupling, right? I mentioned many times, like, oh, it depends on the coupling strength, right? The coupling strength, in another words, is the absorption. So if the molecule give you very large absorption, the coupling strength will be stronger. And also, it will depend on the dipole orientation, as what you said. So if we need the optical field is perpendicular, parallel with the dipole orientation. So if all the molecule is at a 90 degree, yeah, the coupling strength is still very small. So, but we study in a different way. So yeah, we can use amorphous film to demonstrate the planar, but we also study some crystal structure, and we measure the we do the reflectivity characterization on the different angle. We do find they give us different behavior. So at a particular direction, the coupling strength is larger. So yeah, it also shows us the birefringence kind of similar behavior.
All right, maybe we are out of time at this point, but
Yeah.
we can continue discussion
Yeah.
after. Let's thank Bin Liu one more time.
Yeah, thank you.